Welcome to the course Design of Reinforced Concrete Structures. In today's lecture, we'll solve a problem on design of doubly reinforced beams. So, design of doubly reinforced beams. So before solving a problem, first we'll see the steps what you have to follow for the design of doubly reinforced beams. So for a given section of breadth B, depth D, the grade of concrete, the grade of steel and the load. We have to find out AST, that is the area of tension steel, and ASC, that is the area of compression steel for a doubly reinforced beam. So to find out the AST and ASC. So now we will see the steps what you have to follow. So as we have discussed in the previous lecture, what we have discussed, that is a doubly reinforced beam is composed of a singly reinforced beam and an imaginary beam, which consists only of the reinforcement. That is, the first one you will have a singly reinforced beam plus you will have a beam which has only the reinforcement present. So, a doubly reinforced beam is made up of these two. So, first what we'll do is, in the first step, we are going to find out the MU limit and the corresponding AST1, that is the area of tensile steel, considering for a singly reinforced beam the balanced condition. So considering the balanced condition, what you are going to do here, you are going to find out the limiting moment of resistance as well as the area of the tensile steel, considering a balanced section for a singly reinforced beam. So how you can find out the MU limit? MU limit can be found out by using the equation 0.36 FCK B into XU limit here. Why? Because we are considering the balanced section. So in a balanced section, XU is equal to XU limit into D minus 0.42 XU limit. So by using this equation, we can find out the limiting value of moment of resistance. So now, what is the other parameter you have to find out? You have to find out the area of steel reinforcement for a singly reinforced beam for this particular moment, for resisting this MU limit. So how can you find it out? By using the equation MU limit with respect to steel as 0.87 Fy into AST 1 into D minus 0.42 XU limit. So from this you can write down the equation for AST1 as mu limit divided by 0.87 Fy into D minus 0.42 XU limit. So from these equations, that is the MU limit is 0.36 FCK B into XU limit into D minus 0.42 XU limit, you can calculate the limiting moment of resistance, and substituting this limiting moment of resistance in this particular equation, you can find out the area of the steel reinforcement for the singly reinforced beam section. That is, you can find out the AST1. So now we have seen how to calculate the limiting moment and the corresponding area of the steel reinforcement. So what is the next step what you have to do? So now compare MU and MU limit. So if MU is greater than MU limit, then what you have to do? You have to design for a doubly reinforced beam, which you have already learned in the previous sessions. So now what? If moment is greater than the limiting moment, there will be an additional moment which has to be resisted by the compression and the tensile steel. So first, in the next step, that is the second step, we will find out the MU2, that is the additional moment. So the step 2 is to calculate the additional moment, that is MU2. So how will you calculate MU2? MU2 is equal to MU minus MU limit. So by this particular equation, MU minus MU limit, you will obtain the additional moment which has to be carried by the tensile and the compression steel. So now we have known the additional moment. So what is the next step we have to follow? The next step, what you have to do is, we have to, that is what we have to do here, we have to calculate the ASC corresponding to the additional moment. So how will calculate ASC? By using the following equation. That is, MU2 is equal to ASC into FSC minus FCC into D minus D dash. So from this you can write down ASC as MU2 divided by FSC minus FCC. So from this equation, what we can do, we can calculate the area of the compression steel. That is MU2 divided by FSC minus FCC into D minus D dash. So MU2 is nothing but the additional moment which has to be resisted. FSC is nothing but the stresses in the compression steel. FCC is nothing but the compressive stresses in concrete at the place of the compression steel, and D is the effective depth. Okay, and D dash is nothing but the effective depth from the topmost compression fiber to the compression steel. So by using this equation, we can find out the area of the compression steel. So after finding out the area of the compression steel, what we have to do? We have to calculate the corresponding tensile steel, that is the AST2. So the next step what we have to do is, we have to calculate the corresponding tensile steel. The next step is to find out the corresponding tensile steel. So step 4 is to calculate the corresponding tensile steel, which is AST2. So I will find out the corresponding tensile steel by taking the equilibrium condition, the forces of compression steel will be equal to the forces of the tensile steel. So, FSC minus FCC into AC will be equal to 0.87 Fy into AST2. So from this you can calculate the value of AST2 as FSC minus FCC into AC divided by 0.87. So from this equation you can calculate the corresponding tensile steel AST2. So now what will be the total area of tensile steel? That is AST will be equal to AST1 plus AST2. So the total area of the tensile steel can be calculated by adding the area of the tensile steel 1 plus the area of the tensile steel 2. Now what? We have calculated the AST as well as AC as well as the AST. So now what we have to do? We have to calculate the assume a suitable dia of the bar and you have to calculate the number of bars required. Okay, after calculating the number of bars required, the next step what you have to do is you have to calculate the XU and XU limit and compare both the neutral axis depth value and the limiting neutral axis depth value. That is the XU and XU limit value. The next step. So for designing, when you are designing, find out the XU and XU limit and compare XU and XU limit for knowing the type of section. For knowing the type of the section. So if the type of the section is over reinforced, so a over reinforced section if you will get, then what you have to do is you have to go for redesigning if it is an over reinforced section. So these are the steps what you have to follow for designing of a doubly reinforced beams. We'll solve a problem on doubly reinforced beam. So here you can see the question. So what's given in the question? Design a rectangular beam for an effective span of 6 meters. The superimposed load is 60 kilonewton per meter and size of the beam is limited to 30 centimeters by 60 centimeters. Overall, use M20 mix and Fe415 grade steel. So what all are the given data in this? The breadth of the beam is given, that is 30 centimeters, and the overall depth of the beam, that is capital D is given here, which is 60 centimeters. The load which is acting, that is the live load or the imposed load acting on the beam is given, which is 60 kilonewton per meter, and the span of the beam is given, which is 6 meters, and the grade of the concrete is given, which is M20, and the grade of steel is given, which is Fe415. So what you have to find out here? You have to find out the effective depth, and then you have to find out the steel reinforcement, the area of the steel reinforcement which have to be provided. So first here, it is not mentioned whether if it is a singly reinforced beam or a doubly reinforced beam. So first we'll find out whether if it is a singly reinforced beam or a doubly reinforced beam. So how you can find out? You have to know the values of mu as well as the mu limit to know what kind of beam it is. So if mu is greater than the mu limit, then you have to go for the design of a doubly reinforced beam. So first, what are the things you have to find out here? We have to find out the mu as well as the mu limit. So first we'll find out mu. So how we'll find out the maximum moment? So here you can see that is, it is given the breadth of the beam as 30 centimeters and the overall depth, which is capital D, as 60 centimeters. And the span is given as well as the load is given. So how will we find out mu? What is the formula for mu? As it is a superimposed load of 60 kilonewton per meter, you have to find out by using the formula W L square by 8, which you have already studied. So what is W here? W here is nothing but the factored load, which we have to find out now. And L is also already given, that is the span, which is the 6 meters by 8, will give you the factored bending moment. So for finding out the factored bending moment, what is the unknown here? The first unknown is the W. W here is nothing but the factored load. So first what we'll do is we'll find out the factored load. So here, what are the two types of loads we have here? One is the dead load or the self weight of the beam is what you have to find out, and the superimposed load is already given, which is 60 kilonewton per meter. So first we'll find out the dead load or the self weight of the beam. So how will you find out the self weight of the beam? That is the breadth into overall depth into what is the material it is. Here it is RCC. So what is the unit weight of RCC? The unit weight of RCC is 25 kilonewton per meter cube. So from this what you can find out? You can find out the self weight of the beam, which will give you a value of 4.5 kilonewton per meter. So if you solve this, you get a value of 4.5 kilonewton per meter. Now, what is the superimposed load given? The imposed load or the superimposed load. It is given as 60 kilonewton per meter. Now let us find out the total load. So what will be the total load? The total load will be the imposed load plus the self weight of the beam. So 60 plus 4.5, which will give you 64.5 kilonewton per meter. So this is the total load which is acting on the beam, which is 64.5 kilonewton per meter. So in the previous sessions we have already discussed. So while designing, what we have to do? We have to use a suitable partial safety factor, and we have to find out the factored load. So that factored load only it should be used by designing. So now what we'll do is we'll find out the factored load. So how we'll find out the factored load? So the factored load, here what are the two load combinations we have? One is the dead load and the other one is the live load or the imposed load. So what will be the partial safety factor for it, which you have already seen in your IS 456-2000? It is 1.5 into the total load, which is 64.5, which will give you 96.75 kilonewton per meter. So This is going to be your factored load which you are going to use here in the place of W. Now substitute this value of 96.75 kilonewton per meter in the load here, and the span L is given, which is nothing but 6 meters. We can find out the factored bending moment. Substitute the factored load here. So what is the factored load value we got here? 96.75 into what is the span? 6 whole square divided by 8, which will give you the maximum bending moment value, which is 435.37 kilonewton meters. So this is the value what you got for MU, which is 435.37 kilonewton meter. Now we have calculated the MU. So what is the next step? What you have to do? We have to calculate the MU limit. So now let us calculate the limiting moment of resistance. So what is the formula we have learned? It is 0.36 FCK B into XU limit into D minus 0.42 XU limit. So you already know the value of FCK which is given in the question. P is already given. And what are the unknowns here? You have to know the XU limit and you have to know the D. Why you have to know the D? Because here the overall depth D is given as 60 centimeters, but the effective depth is not given. So first let us find out the effective depth D. So for finding out the effective depth D, what I am doing is let us assume an effective cover of 60 mm. Here what? I am assuming an effective cover of 60 mm. So from assuming an effective cover of 60 mm, I am going to find out the effective depth D. D is nothing but the effective depth. D will be equal to the overall depth minus the effective cover. So what is the overall depth? It is 600 mm minus 60 mm will give you the effective depth, which is 540 mm. So now I have got the value of the effective depth D as 540 mm. Now what is the next unknown here? To find out the limiting moment, that is XU limit. Next is what you have to find out is we have to find out the XU limit. So how will you find out the XU limit? The XU limit will be based on the grade of the steel. So what is the grade of the steel here? The grade of the steel is Fe415. So what will be the XU limit value? It will be 0.48 D. So 0.48 into D. What is D here? D is 540 mm. So if you calculate this, you will get a value of 260 mm. So the XU limit value you are going to get value of 260 mm. Now substitute both the D as well as the XU limit values in this particular equation so that you will get the limiting moment of resistance. So MU limit will be equal to 0.36 into FCK is 20 into B. How much is B? It is 300 mm into XU limit. What is the value of XU limit? It is 260 into D. What is D? How much is D? It is 540 mm minus 0.42 into XU limit, which is 260. So if you will calculate this, you will get an MU limit value of 241.5 kilonewton meter. we get a value of 241.5 kilonewton meter. So from this what you can observe that mu is greater than mu limit. So if you see the value of mu, it is 435.37 kilonewton meter. And what is the value of mu limit? It is 241.5 kilonewton meter. So mu is greater than mu limit. So if mu is greater than mu limit, so for what you have to design? You have to design for a doubly reinforced beam. Have to design for a doubly reinforced beam. So for designing for a doubly reinforced beam, so in the previously we have seen what is the step 1? The step 1 is to find out the mu limit. So already we have calculated the mu limit. So what is the value of the mu limit? What we have got, it is 241.5 kilonewton meter. So this is the mu limit value what we have got. Now what we have to do? We have to find out the area of the tensile steel corresponding to this particular moment. So let us find out the AST1. So how will we find out? mu limit is equal to 0.87 Fy into AST1 into D minus 0.42 XU limit. So from this, AST1 will be equal to mu limit divided by 0.87 Fy into D minus 0.42 XU limit. So you know all the values. You know the value of mu limit which we have calculated here. You know the value of Fy which is given in the question. D is already found it out previously and XU limit value is also calculated. So substitute all the values here so that you will get the area of the steel reinforcement 1. So what is the value of mu limit? It is 241.5 into 10 to the power of 6 divided by 0.87. Fy is 415 into D is 540 mm minus 0.42 into 260 mm. So if you calculate this, you get a value of 1556 mm square. That is the area AST1, area of tensile steel corresponding to this particular moment will be 1556 mm square. So now we have calculated the AST1. So what is the next step what you have to follow? You have to calculate the additional moment mu2 which has to be carried by the compressor and the tensile steels. So how will calculate mu2? mu2 is equal to mu minus mu limit. So how much is mu? We have calculated previously. It is 435.37 kilonewton meter minus mu limit. What is the mu limit value? It is 241.5 kilonewton meter. So if you calculate this, you get a value of mu2 as 193.87 kilonewton. So this is the additional moment which has to be resisted by the compression and the tensile steel. So now after finding out the additional moment, so what is the next step what you have to do? You have to calculate the area of the compression steel and the area of the tensile steel. So now first let us find out the area of the compression steel. The next step what we have to do is we have to calculate the area of the compression steel. That is, we have to calculate the ASC corresponding to this moment 2, that is mu2. So let us find out the area of the compression steel. So how you will find out? By using the equation mu2 is equal to ASC into FSC minus FCC into D minus D dash. So from this you can write down ASC as mu2 divided by FSC minus FCC into D minus D dash. So you already know the value of mu2, which is 193.87 kilonewton meter. You already know the value of D. So what is the value of D we have got? It is 540 mm. And the value of D dash also. What is the value of D dash we have assumed? That is the effective cover as 60 mm. So what are the unknowns here? The unknowns here are FSC and FCC. So first we find out the FCC. So how FCC can be calculated? You know the formula which we have already learned, that is 0.45 into FCK. So what is the FCK here? FCK is nothing but the grade of the concrete, which is 20. So if you solve this, you get a value of 9 Newton per mm square. Now let us find out the value of FSC. So for finding out the value of the FSC, in the previous classes that we have already discussed, there are two ways. So first what we have to do in one way, if you use the stress strain curves for HYSD bars or the stress strain curves for the steel reinforcement. So what you can do, first what you have to calculate the EFC. So how will you calculate EFC? By using the formula 0.0035 into 1 minus D dash by XU limit. So you know the values of D dash and XU limit. Substitute here. So 0.0035 into 1 minus D dash is 60 divided by XU limit you have calculated previously, which is 260. So from if you solve this, you get a value of ESC as 0.002695. So now what you have to do from the stress strain curve for steel reinforcement, which is given in IS 456-2000, what you have to calculate the FSC corresponding to this particular strain. So if the same value of ESC strain is not given, then you have to go for the interpolation and you have to find out the FSC value, which we have already learned in the previous sessions. So if you do the interpolation and if you calculate, you can get the FSC value as 353 Newton per mm square. So this is the FSC value. So all of you have known all the values. Substitute all the values in this particular equation. So if you substitute, what you will get? AC is equal to mu2. What is mu2 here? It is 193.87 kilonewton meter into 10 to the power of 6 divided by FSC. What is the value of FSC? It is 353 minus FCC. What is the value of FCC? It is 9 into D. What is the value of D? It is 540 minus D dash. What is the value of D dash? It is 60. So if you calculate this, you get a value of AC as 1160 mm square. So this is the area of the compression steel for the additional moment mu2. Now let us find out the corresponding enzyme steel, that is AST2. So how will we find out the AST2? That is by equating the total compression steel forces to the tensile steel forces. That is AST into FSC minus FCC will be equal to 0.87 Fy into AST2. So from this we can find out AST2. That is AST2 is equal to AC into FSC minus FCC divided by 0.87 Fy. So we have already calculated the value of AC. What it is? It is 1160 mm square. You already have known the value of FSC minus and FCC. So what is the value of FSC? It is 523 Newton per mm square and FCC value is 9 Newton per mm square divided by 0.87 into Fy. Fy is nothing but the grade of the steel, which is 405. So from this you will get a value of AST2. So what is the value of AST2? If we calculate this, we will get a value of 1134 mm square. So this is the AST2. Now let us find out the total area of tensile steel. steel. So how will you find out the total area of the tensile steel? It is AST1 plus AST2. AST1. So what is the value of AST1? It is 1556 plus AST2, which is 1134. So if you calculate this, you will get a total value of AST as 2690 mm square. So this is the total area of the tensile steel, which is 2690 mm square. Now we have found out the ASC, AST1 and AST2, that is 1134 mm square, and the total AST, which is 2690 mm square. Now what? Now I have known the effective depth, the area of compression steel and the area of the tensile steel. Now I will find out the number of bars required for this particular compression steel and the number of bars required in the tensile zone. So for that, what I will do is I will assume a suitable diameter of the bar. So first let us consider what I am considering. I am considering the tensile steel. That is the AST, which is got 2690 mm square. So here what I am doing, I am assuming. So let us assume the dia of bar is 28 mm. So now I will find out the number of bars. How? N into ID square by 4 is equal to 2690 mm square. So what is the D here? 28 divided by 4 is equal to 2690. From this I'll get a value of N as 4.36 approximately. You can take 5. So how many bars we are providing? We are providing 5 bars of dia 28 mm in the tensile zone. Now in the similar way, let us find out the number of bars in the compression zone also. So for that, what I am doing, I am assuming the diameter of bar as 20 mm. For what? This is for the compression steel. So in the similar way, find out the number of bars. N into pi d square by 4 is equal to AC. So what is the AC? It is 1160 mm square. So what is D here? I am assuming that is D is 20. So divided by 4 is 1160. So from this we will get a value of N as 4. So how many bars I am providing here? I am providing 4 bars of dia 20 mm in the compression zone. So this is the way how we have to design. So the final step, what you have to do is, while designing, you have to check for the maximum area of the tensile reinforcement. So now let us check for the maximum area of the tensile reinforcement. Let us check for the maximum area of the tensile reinforcement. So check for what? For the maximum area of the tensile reinforcement. So how do you find out the maximum area of the tensile reinforcement? You have the formula, which is B into D. So B is the breadth and D is the overall depth. So it is 0 into, what is the B? It is 300 mm into, what is the D here? It is 600, 200 mm square. So this is the maximum area of the tensile steel. So here, what is the tensile steel what we have got? That is 2690 mm square. So it is greater, the maximum area is greater, hence the check is okay. Hence the design is okay.